Okay, Assalamu alaikum, welcome you all to this webinar. We are glad to have Professor Morale Navarro to give us this talk about DarKnight training machine learning models with the private data. Let me give you a brief introduction about Professor Morale. Professor Morale Navarro is a professor in Ming Che Department of Electrical Engineering and in the Department of Computer Science at the University of Southern California. His research group tackles a wide range of computer system design challenges related to energy efficiency and security and privacy. He was inducted to the Hall of Fame in 3 prestigious computer architecture conferences, ESCA, Micro, and High Performance Computing, HPCA. He serves as a technical program chair for HPCA 2021, the general co-chair for ESCA 2018. Before he joined USC, he worked at Intel Microprocessor Research Lab from 2001 to 2007, where his work led to the first 3D microarchitecture paper and also influenced Intel's Turbo Boost technology. In 2007, he was a visiting researcher at Nokia Research Center, where he worked on phone-based wireless traffic sensing using virtual trip lines. In 2020, he also was a visiting faculty scientist at Facebook, where he designed a checkpointing system for distributed training. Professor Navarro co-authored textbook in parallel computer organization and design, which is widely used for teaching basic and advanced principles in computer architectures. He received his PhD in 2001 from University of Michigan, Ann Arbor, and he is a senior member of IEEE and ACM. Regarding today's talk, Dr. Navarro is going to talk about DarKnight, which is a framework for training large deep neural networks while protecting the privacy of data and computation integrity. DarKnight relies on the cooperation between the trusted execution environment and accelerators, where the trusted execution environment provides privacy and integrity and verification, while accelerator do the bulk of computation. DarKnight actually uses an encoder scheme that is designed to support both training and inference. I will leave the floor to Professor Navarro to talk to deliver his talk, and then we are going to take a round of Q&A. Professor Navarro, the floor is yours.
Thanks, Abdulaziz. So thank you for, I know it's quite late in Saudi. Thanks for joining the talk late in the night. What Abdulaziz did not mention is that not too long ago, Abdulaziz was in my research group at USC as my PhD student, and he graduated 3 years ago now or so, and he is back teaching, and I'm sure he's doing an excellent job on computer architecture teaching. And so I am quite happy to see him and also to get an opportunity to talk to many of you. Although it's a virtual setting, it makes it harder to physically interact and talk. But if you have any questions, please raise your question and we can answer them in the middle of the talk, or whatever Abdulaziz decides is the appropriate mechanism. So with that said, I wanted to talk about one specific topic, which is basically how do you do machine learning algorithms training and inference using data that is private. So the basic principle here is that we all have, on our phones, for example, literally tens of thousands of pictures, and we want to automatically tag those images. This is one example. And so you want to send it to a server to tag those images with appropriate characterization, but you don't want to send those images to a server that you don't know or you don't trust. And therefore, if you want the server to tell you, hey, there is a particular feature in this image, say a picture of a bird or a picture of an animal, you need to show that image. Otherwise, how is the server going to tell you what that image contains? So it's a chicken and an egg problem. You don't know how to solve the problem. You want to use a service, but you don't know how to do it without disclosing your data. That has always been a fundamental problem. With that as being said, let me talk about the solutions that we have been working on. And I'll touch upon one solution primarily today, given that we only have about 45 minutes or so left for the talk. So with that, so let's look at the motivation. So clearly by now, all of you know that deep learning has many applications in our daily lives. And so this includes, manufacturing, healthcare, transportation, e-commerce, automobile design, customer services, insurance. A whole host of industries now rely on machine learning as one of the driving force behind their data analytics. Now, if you look at these industries that I listed here, there is no computing industry there directly. It's all manufacturing, healthcare, insurance, customer service, transportation, and so on and so forth. And what is common to all of them? These are people who have literally millions and millions of bytes of data generated at a very high frequency. And unfortunately, they are not computer scientists, as in they are not the people who are going to take this data and somehow figure out what models to use and try to train those models using the data that they have. Because these people have lots of data, but not necessarily the experience required or the expertise required to truly train these models and use these models for inference, it's very common today for all these companies to rely on third-party vendors. So for example, if you're familiar with Amazon, Amazon provides a cloud-based inference system. Google has its own cloud-based inference system. Facebook uses their own inference systems. So all these are basically mechanisms by which you can upload some information to the web, to a cloud, and they will provide you some of the services. So they're essentially sharing, in other words, these companies are sharing their data with experts who design these models so that they can be trained and processed in the cloud. So this seems to work well. I mean, you don't have to be an expert to use an ML model. You assume that the cloud gives you the capability. There's a simple programming API you use, upload it to the web, and everything gets done. That's what you would think. But then this is what we call outsourced ML. Basically, the machine learning has been outsourced to third-party entities in the cloud. And there are two primary challenges that I think that must be solved in order for these outsourced ML to become very popular. One is data privacy. And as I hinted at the beginning, you don't want to disclose your data directly to the cloud just to get their service. And therefore, you are quite hesitant to actually send all your information to the cloud because, even if you trust the cloud provider, let's say you do trust the Googles or the Amazons, they could be hacked. And therefore, there's a possibility that even if you trust the cloud provider, the machines that you're running on may not necessarily be trustworthy. And a related problem is computational integrity. And what that means is that imagine that you send the data to the cloud and it is mostly automated systems, and it has given you some output, some results. How do you know that the results are actually correct? Because this is not something that you control. These machines are controlled by the cloud, and therefore it's possible that some of these machines, again, because they're compromised by either hackers or other sort of entities, they could give you intentionally wrong results. And therefore, and some of these results, intentionally wrong results, are very difficult to actually verify. For example, it's not as simple as 2 + 3 = 6, and then oh, that's wrong. It's going to be much more subtle in terms of how they can change the computational outputs. And so these are the two primary and fundamental challenges that one must tackle. And then the last but not the least is that data privacy regulations are coming. So already there is a substantial discussion across the world in all kinds of government agencies about the data privacy aspects of high big tech corporations. So we can see that policy is going to come in where they are going to require some sort of privacy guarantees. And so the question is, as a technologist, as people who are not policy people like myself, as technologists, as researchers, we were interested in figuring out, is our technology ready for these privacy regulations? So that's sort of what drives the research that we are interested in. So with that sort of a motivation, I wanted to dive into the background work of what some of the things that we're going to do require a little bit of understanding of some of the basic concepts. I assume for the purpose of this talk that you understand a deep learning or a machine learning model means, and therefore I won't go into a lot of the detail, but there is some other background that I need to give you, which I will provide. So one of the background materials that's necessary to understand the rest of the talk is trusted execution environments. Trusted execution environments, also called secure enclaves, is a hardware isolation capability provided by CPUs. So in particular, Intel provides something called SGX. So if you're interested, you can actually look at this paper, Intel SGX Explained. And what that does is that it creates a protection zone within your CPU where you can execute applications, store the data inside that protected zone, and that protected zone is called enclave. And the enclave is a construct that is supported by many modern CPUs, including Intel, and Intel calls it SGX. ARM processors use a slightly different terminology called trust zone. AMD has their own mechanisms for providing these enclave capabilities. And one of the interesting aspects of these enclaves is that these enclave executions are completely isolated from the operating system overview. So what that means is that if you are, let's say, a root user, you somehow broke into the computer system, you have an administrative access, and you can actually become the super user, even then, you are not able to read the data that is actually inside the enclave. And you cannot see the instructions executed inside the enclave by an application that's inside the enclave. So in this picture, as you see, there's basically sensitive data that, let's say, that's your image that you're interested in, and the signed application. And this application could be a machine learning model, or it could be any other application that you are interested in executing. And if you put this application inside the enclave and you put the data inside the enclave, essentially you sealed off this information from outside entities, including a system administrator. They can kill the enclave. They can basically, shut down the machine, but that's not harmful in the same way as you disclosing the information. And therefore, it is providing you information. It is providing you a capability where you can execute stuff without being watched over by some root user. And so the data that is stored in these enclaves is encrypted. The data that is stored is basically encrypted, and this is not accessible to any code outside of the enclave, as I just said, including the operating system. So essentially, when you create an enclave, you essentially create a trust mechanism. Say the enclave gives you a key as a end user. You use the key, and you can verify that the computations that you're being performed are not being leaked. And you can also verify that the data that is actually inside the enclave is not being leaked using this key that you exchange as part of your enclave creation. So that's what enclaves do. And in this particular talk, I'm going to use Intel SGX as the enclave mechanism, but it's not necessarily has to be only enclave. It could be many other mechanisms. They have slightly different capabilities and mechanisms and logistics, but fundamentally they provide some of the capabilities that we are interested in. Well, the Intel SGX has this computational integrity mechanism. Basically, any computation that's done inside the enclave is guaranteed to be correct as long as the hardware is correct. As long as the hardware is designed correctly, it will provide the right result. And as I said, it will provide you a code and data privacy without the operating system looking into it. But the problems with the current SGX implementation is they tend to be very CPU centric. And they also have severe memory limitations. So for example, the implementation of SGX today supports only 128 megabytes of memory. So if you go back a couple of slides ago, this data piece that I mentioned, it cannot be more than 128 megabytes. If it is more than 128 megabytes, then you have to store that data outside the enclave using encryption in the memory. And then the enclave has to reach out to the memory and decrypt the data and bring it into the enclave. It's a very slow and expensive process. So if you can keep your sensitive data to under 128 megabytes, you don't have to go to the outside of the enclave, and you can stay within the enclave, and your performance is much better. And hence you have these two limitations, that this is CPU and it has only 128 megabytes of memory. That means that vast majority of complex DNN models are going to have a difficulty actually being to fit within the SGX limitation. So with that brief background, let me sort of describe the DarKnight. This is the technique that we have worked on, and it is a part of our goal to use these SGX, these Intel enclave capabilities and acceleration mechanisms to solve some of the machine learning problems that I alluded to earlier. So what's the basic solution? The simplest solution is to say, well, I have an enclave in the cloud. I can exchange a key between my phone and the enclave in the cloud. And I say, here is my data, here is the model I'm interested in, train it and put everything inside that enclave. And nobody else can see what is happening inside the enclave. So, okay, great. Now I have the data in there. I have the model inside the enclave, and therefore I don't need to do anything special. It's all privately trained or privately inferred. But the problem is that the performance overhead for using an entirely CPU-centric system is quite extensively limiting. Because if you are familiar with machine learning models, most machine learning models tend to be very, very GPU-centered. They actually operate with GPU as the foundational computing block. And in fact, more recently, for example, Google has talked about, Google has released tensor processing units, TPUs, which is a special, even further specialized accelerator for doing machine learning models. And so, as you can see, that if you limit yourself to just a CPU-centered TEE, you're going to be somewhat left behind in terms of your memory, in terms of your model performance, both in terms of how long it takes to train it, how long it takes to do inference on that model. So this is the challenge. And what we have done is we looked at how much time does an application like a deep learning model spends inside the various components within its computation. And what we found is that most of the computationally expensive operations in this system, in this deep learning models, tend to be very linear. So what does a linear mean? Means matrix algebra. So you have a matrix multiplication, matrix vector multiplication. These are the kinds of tasks that are very commonly used in machine learning models. And again, if you've taken a deep learning course, you know that the entire model parameters are represented as a weight matrix. And therefore, matrix operations are foundational. And vast majority of the computations tend to be linear inside these deep learning models. And these linear computational operations, such as matrix algebra, tends to be very, very fast on GPUs. So if you can somehow execute these linear operations on the GPU, then you can get substantial performance. And if you execute nonlinear operations, for example, machine learning models have some nonlinearity, such as ReLUs or sigmoid functions. If you're familiar with some of those terms, you know that those are very small number of such operations. And they don't get much benefit in a GPU. So it doesn't really matter where you execute those small set of instructions. But for the linear operations, you really will benefit if you are able to execute it on a GPU. But the problem is, I don't want to send my data to the GPU because there is no TEE or any kind of enclave capability on the GPU. So how do you solve this dichotomy is really the challenge. So we are interested in offloading computationally intensive operations like matrix algebra to the GPU. And our solution is going to use the CPU and in particular, the trusted execution environment for nonlinear operations only. That's the deal. That's how we're going to split the work. We're going to execute the linear operations on the GPU and the nonlinear operations on the CPU. But at the same time, we are not going to disclose your input data to the GPU. So now we have another problem. We want the GPU to do matrix algebra, but we don't want to tell the machine or the GPU what's inside that matrix. Foundational problem. How are you going to do computation if your data is not really visible? So we're going to look at what is called a data encoding and decoding strategy for dealing with this problem. So here is what the DarKnight provides. Before I go into the details, I wanted to give you what is the capability of a DarKnight. The capability of a DarKnight is that it provides perfect privacy. So what that means is, if you imagine that if your input image is X, and what the GPU is seeing is some modified version of X, which is what we're going to do, which we'll call X prime or X bar. The mutual information between the information that is delivered to the GPU and the information that's actually there, which is the image that you have, is going to be 0. So we guarantee theoretically that there is no information leakage between the image and what the GPU sees. Second, if you have k GPUs, DarKnight provides you k-1 secure. Namely, if any of the k-1 GPUs in the system send erroneous results, it can detect it. And 3, DarKnight is also collusion safe. What does collusion means? Collusion means that, let's say, 3 of the GPUs are going to communicate with each other and help each other out, and then maybe extract information from that. And we're going to also provide a guarantee that when m GPUs collude, where m is a function of the number of GPUs k, even in that case, we guarantee that no information will leak. And so keep this in mind. M is the number of collusions that we allow. K-1 is the number of GPUs that we can actually tolerate errors on. And we have mutual information guarantees of 0. That's what we have. So what's in there? So we're going to look at how this whole system is going to work. And I'm going to use a very high-level pictorial description first to give you the 8 foundational steps that we are going to execute in the system. So this is the client. Client is, for example, your mobile device is going to essentially take a set of input images that it wants to protect. And it is going to encrypt them using some kind of a key that is exchanged with the TEE. So this computer here is representing a TEE, or enclave, basically. So it encrypts the images and sends it over to the enclave. This encryption provides you a guarantee that nobody can listen on the channel, let's say the data channel that is carrying your data packets, because it's all encrypted. Once inside the SGX, once the data is received inside the SGX, then the SGX uses the key, because you have exchanged the key with the client, using a decryption mechanism to recover the images. But remember, now the images are now fully raw images, but they are inside the enclave, so nobody can actually see them. And this is where it gets interesting. It takes those images and linearly encodes those images to create essentially an obfuscated or a confused image, if you want to think of it that way. So it creates an encoding of the images to create an obfuscated image, which is then creating this what we call linear encoding of inputs. This encoded data, which has now no information, so and this is the guarantee that we provide. This encoded data has no information regarding the original input image. In other words, there is 0 information leakage between the input data and the encoded data. And that encoded data is sent to the GPU. And in step 5, we do all kinds of linear operations on the GPU. And these linear operations could be weight times input X, like basically matrix vector computations. And once you have computed on the encoded data, you send the results back to the GPU, to the SGX. And in step 7, we can decode the results. And this is really interesting, because as long as we can decode the result, then we are good. It doesn't matter what the GPU sees and how it is computing. As long as we can decode the results correctly, we are in good shape. So therefore, the step 3, which is the linear encoding and decoding, work in pair, work together, so that the encoding process knows how the decoding is going to work, and the decoding process knows how the encoding is going to work. And therefore, by using this decoding, we can now extract the information that we need that the GPU has computed. And finally, we perform all kinds of nonlinear operations within the enclave, like such as ReLU, max pool, standard operations that you see in any DNN operations. And this process is repeated again and again. If you're doing training or if you're doing inference, that's it. You just do one forward pass and you're done. Okay, so these are the steps. What's inside the encoding and decoding? So this is really the 2 key elements, step 3 and step 7. So I'm going to give you a very simple example to show you what is inside step 3 and step 7, so you have a sense of what this problem is going to look like. So take a look at data encoding process. Imagine that you have 4 input images that are actually sent to the cloud using the key-based encryption mechanism. The enclave decodes them, decrypts them, generates these 4 images. I call them represented by 4 vectors, x1, x2, x3, x4. And imagine that we have 5 GPUs for the purposes of this discussion. The first thing the enclave does is it generates a set of secret keys called the random scalars, alpha ijs. So it's going to generate these random scalars, which are secret because nobody else outside of the enclave will know them. And it also generates a random uniform vector called R, and we're going to explain how this is actually going to be used in just a second. So it's going to now generate a set of random scalars and a random vector, and it has 4 input images and 5 GPUs it can use to do its computations. So let's see what it does. The enclave basically takes these 4 images and multiplies each image with a particular random variable alpha ij. That's alpha 11 example here. Alpha 12 is multiplied with x2, and alpha 13 with x3, and so on and so forth. And then finally, we multiply alpha 15 with a random vector R, or a random matrix R, and you generate essentially what we call x1 prime or x1 tilde, as is shown here. And that is how it looks like. And in fact, this particular sequence of images and this output is exactly what the enclave actually generates. And that is what is sent to the GPU1. So you can clearly see visually that this looks like a white noise. There is no information in this image. It's just all random data pixels that you have. I can do the same thing again, but a different set of random scalars, alpha 21, 22, 23, and so on. And then I generate x2 prime, which is sent to the GPU2. Same thing with the third. Basically, you take alpha 31, 32, 33, 34, and you multiply all of these with different randoms or variables, and then you get a x3 prime. x4 prime is generated the same way, and x5 prime is generated the same way. And so now you have generated 5 random x tildes, which are then sent to different GPUs 1 through 5. Okay, so once these GPUs are operating on this random noisy data, they don't really know what is in this input information. They have no idea what's actually constitutes this particular image, or GPU2 doesn't know anything about what is inside each of this image because it just looks like random noise. But this is the data encoding pass. Once the data encoding is done, how do you do this encoding from a mathematical perspective? From a mathematical perspective, your input is X, consisting of 4 images, X1, X2, X3, X4, and then the random noise that I used, which is R. And we created a matrix of random values, which is alpha 11, 12, 13. So that's basically this image. If you look at it, these alphas form one set of matrix, right? And then x1, x2, x3, x4, and R forms a different matrix. And hence, all we did for encoding is just simply multiply this X with A transpose to get your x1 prime, x2 prime, x3 prime, x4 prime, and x5 prime. It's a standard linear algebra, nothing special you should be able to see. It's very simple at this point in time. So this is what we have done for encoding of the data. And what does the GPU see? The GPU sees x1 prime, x2 prime, x3 prime, x4 prime, and x5 prime. And imagine that you're doing an inference. For the purposes of this simplicity, I assume that the data is, we are interested in inference only. What is inference? Inference takes the values of these images x and multiplies that with the weight matrix W to generate a value that is the actual prediction. So it's usually W times x1, W times x2, but instead the 5 GPUs computed W times x1 prime, W times x2 prime, W times x3 prime, and so on and so forth. And here I want to clearly show you that our state that W is known to be public. In other words, the model itself is known and the GPUs know what the model is. There's nothing to protect in the model itself. It's the axis that we are interested in protecting, which is the input images that we are interested in protecting. So what do we need to do when the GPU computes this y tilde? What do I need to do to extract my original values? Remember, we did x times A transpose. We multiplied that with W. We got W times x times A transpose. That's what we have essentially computed. All we need to do is to multiply it with A transpose inverse so that you get your WX back. It's very straightforward. And so the results we're interested in can be obtained by simply multiplying the values returned from the GPU with an A transpose inverse. And remember, A is a secret matrix, right? This is a secret value that we are not going to disclose to anybody. Therefore, you can now decode and recover the WX values inside the machine, inside your enclave. So I know, there is a lot more to be done on the backward propagation also, which is basically when you're doing the training. But in the interest of time, let me kind of skip over some of the details for the purposes of the data encoding. But the basic principle is that when you are doing the backward propagation is a lot more complicated because you are now trying to compute the gradients of all the images as they propagate so that you can actually update the weight matrices. And hence, there is a fundamental problem that each of these gradients is computed with respect to a particular image. And hence, we need some sort of a new encoding mechanism for this process. And I refer you to the micro paper to see all the details of what we have in the backward propagation. So I'm just going to skip over a little bit of the details here. Okay, now let me sort of say that we have a mechanism for encoding and decoding the data for forward propagation and backward propagation. And in this mechanism, all the inputs x1, x2, x3, x4 are always protected. Remember early on, I talked about integrity checks. What does that mean? Let's say that you don't trust these GPUs. They are out in the cloud. You don't know if they're producing the right result or not. And so you want to verify that the computations performed by the GPU are in fact the true computations. How do I verify the computations performed by the GPU? It's relatively straightforward. All we do is instead of using 4 images, I use only 3 images in this example. Let's say that I have 3 images that I took out of the 4, and I computed them using 5 different equations, as I just showed you here. So I have 5 equations and 3 input images, x1, x2, x3. What does this tell us? You have created essentially redundancy in your computation. And because you created redundancy in your computation, effectively, you have 5 linear equations of which there are only 4 unknown variables, x1, x2, x3, and the random matrix R. So we have only 4 unknowns and 5 equations. What does that mean? You can compute every output in 2 different parallel manners. You can compute it one way or the other way. And therefore, if you compute every result in 2 different ways and you compare, and if they don't match, you know there's a problem. And hence, you can create this redundancy in a very nice way. And anytime you are not sure, you don't trust the GPU, you do a quick check. Say, I'm going to compute the result of this 2 different ways. So I will do one set of equations to generate one result. I use a different set of equations to generate a second result. And in both ways, I should get identical result. And if I don't, some of the GPUs are lying to me, and therefore I know there's a problem in the system. So in fact, you know, as you may all well know, the most important aspect of integrity verification is to, first of all, detect that there's a problem. Once you detect the problem, it's easy to actually solve the problem in most of the scenarios. So we can detect it very quickly, and we can go from there. Now, we can also do colluding GPUs. For example, imagine that we have a set of GPUs that are actually becomes friends with each other, and they say, hey, I send you my data, you send me your data. Maybe between the two of us, we can actually extract the x1, x2, x3, even though we only see x1 prime, x2 prime, and x3 prime. And in fact, the solution to colluding GPUs looks a lot like what I showed you before, which is simply add more noise and create additional equations so you can solve any kind of collusion related activity in this system. And so in the case of a colluding GPUs, essentially you take three of these images, and we create two sets of random vectors, R1 and R2. And therefore, in this system now, there are three images, x1, x2, x3, and two random variables, R1 and R2. And hence, any two GPUs collude, they can't actually cancel out the Rs, because there is one R1 and one R2. And even if two GPUs try to talk to each other, they can't extract R1 and R2 together. You need a collusion of more than two GPUs, let's say GPU 3, 4, and 5. So again, as long as the collusion is limited to a subset, we can create multiple of these random variables, and then you will not be able to detect it even after collusion in this system. So in summary, in a system with K prime GPUs, DarKnight provides data privacy and computation integrity by tolerating up to M colluding GPUs, where you basically have this notation that is shown here. As long as you have K prime GPUs is the K plus M plus 1 is less than or equal to K prime, you will always guarantee the correct output and protect the privacy, check the computation integrity, and tolerate the collusion, and provide all the perfect privacy guarantees that DarKnight originally provides. There's a lot of detail that in the way the system works, and I highly encourage those of you who are interested to kind of take a quick look at the paper. It appeared at Micro this year, about a month ago. Okay, all of this is great. And obviously, we are not just theory people. We want to build systems. We want to test systems and see how good they behave. And so we built this system using an Intel Coffee Lake processor, which is a E2174G processor, which has an SGX support. And we use the NVIDIA's GeForce GTX 1080 Ti GPUs. And we have a 40 gigabits per second infinity network switch between the TEs and the GPU. And we are running three different models. In this case, we are running a DNN model called VGG. It's a very large resource-consuming DNN, lots of matrix operations. This is a primary candidate for what we do because matrix operations are very slow. We should be able to get a good performance. The second one is ResNet 50, which is also another one of the ML models. And then the third one is MobileNet V2, which is a worst-case scenario for our design because MobileNet does not actually have a lot of matrix algebra because they created this network to run on small form factor devices. So they minimize the linear algebraic computations in the system. So with that in mind, as you can see, the training time for different networks, which is VGG, ResNet, and MobileNet. So we have two sets of results, baseline and DarKnight. Baseline and DarKnight is shown for each of these models. Baseline is when you run the entire model within the TEE, just the original assumption that I showed you. Therefore, you are not able to take advantage of the GPUs. You are only running within the TEE. And as you can see that if you look at the linear operations, it took 0.84 seconds in the baseline. And on the DarKnight, the linear operations are performed in 0.04 seconds. Substantial improvement, right? And then the nonlinear operations in the baseline took 0.16 seconds, but we actually take a little longer in our DarKnight, because the nonlinear operations are running within the enclave. There's a limited amount of compute capability, and therefore we are essentially running a little bit longer on the nonlinear operations. But we are still far better on terms of your linear operation performance. And here is the cost for encoding and decoding, additional cost for encoding and decoding, and the communication overheads. So these are things that the baseline does not have. Therefore, there are zeros in this case. Okay, given that, what's the speed up that we get in total? So the baseline is fully implemented in a trusted execution environment. And we have, I won't go into the two different sets of details, but basically we have two different experimental setups. The pipeline model assumes that while the SGX is doing some encoding, some other input images can be processed simultaneously. So you kind of pipeline the encoding process with the cost of doing the SGX, the GPU computations. And so in the pipeline model for VGG16 for linear operations, we get 158x speed up. And for nonlinear operations, we get just a tiny bit of overall speed up. But overall, you get a total of about 12x speed up when you run the entire end-to-end training of a VGG16. And if you remember MobileNet is a system which does not have a substantial linear operations, and therefore it is not likely to get a substantial improvement. And of course, as expected, it only gives you 2.92x speed up overall. And so basically we can get something in the ballpark of 5x in the base or baseline in non-pipeline version, and 6.5x in a pipeline implementation. Okay, so sort of conclude, our proposed framework, which is DarKnight, utilizes trusted execution environment for providing privacy. It utilizes GPUs for linear operations, and it can use the CPU for nonlinear operations. And by using TEEs and GPUs together, it can perform integrity verification and integrity checks. And I encourage, again, as I said, see the paper for privacy proofs and encoding strategies, quantization mechanisms, how does it deal with aggregation mechanisms, and all the implementation details are all in the paper. So with that, I will stop so that you guys have, you folks have a few minutes to ask questions or anything else that you might have.
Thank you, Professor Anvaram, for this talk. I have to answer questions here. The first question asking about the complexity of matrix multiplication, both done for encoding and decoding. How complex is the matrix multiplication for encoding and decoding?
Yeah, so basically, if you look at this operation that, so this is what I think they were referring to, which is W times,
yes,
not that. Yeah, so it's this X times A transpose is what they were talking about. So if you look at what we are trying to do here, this operation is a scalar times multiplication of a vector. It's a scalar vector multiplication, a scalar vector multiplication. So it's a linear in terms of the size of the matrix itself. So it's not a matrix algebra. It's a straightforward scalar multiplication of each element in a matrix. And then this is an addition, alpha 1,5 times R is an addition. So all of these mechanisms are order n complexity. And what is the GPU doing is actually doing much more like matrix vector multiplications, which is the W times X prime. So it's an order n squared kind of an operation. And therefore, the computations performed within the CPU are substantially lower dimension and lower complexity than the GPU computations.
Okay, thank you. We have also another question about, it asks, do we have, do the cloud provider like Azure or AWS or Google have ready resources for enclaves or trusted execution environment?
Good question. And in fact, because this problem is so severe, they have actually made enclaves available within the cloud systems. So in fact, if you're interested in requesting an enclave from the cloud, not just a standard virtual machine instance, but a secure virtual machine like a trusted enclave, you can actually get that from most of the cloud providers such as AWS and so
on. Another question here. It's a follow-up question to the first question. So you answered the question about the complexity of matrix multiplication for encoding. What about the decoding?
Oh, so the decoding is, yeah, go ahead.
And also the question also asked about what about the computation of the inverse of the matrix, computing the inverse of the matrix.
Oh, sure. So I think there are two things that are being referred to, which is I have to first of all compute A transpose inverse and then multiply that with this. So there are two sets of operations that are required. So the first thing is, as long as, remember, this A, matrix A is something that you choose. It's a secret set of matrix scalars that you choose. So as long as you create a matrix of these alpha ij's that are well formed, you will always find an A transpose inverse very quickly. But more importantly, remember that before you execute any of this system, there is nothing that prevents you from generating these random values, alpha ij's, a priori. Before you start the execution, before you set up the system, imagine that you created the enclave, and the enclave comes with a whole set of random numbers and the random keys. Therefore, even though, first of all, this computation is relatively quick because you can actually control what the random variables you want to use in your matrix. And two, you can actually generate them offline in a sort of an offline phase, which makes this computational aspects completely irrelevant. And third, which is what I talked about, the pipeline versus non-pipeline implementation. Imagine that you are computing this WX A transpose times A transpose inverse inside your GPU, inside your TEE. Nothing is preventing you from using the GPUs for a different set of images or a different layer. Imagine that if you have two DNN layers, the first layer is being two sets of images. The first set of images is being performed on the GPU. The second set is being decoded on the SGX. And then you kind of toggle back and forth in a pipeline fashion. And that way, even if it takes you a little bit longer, because the cost of decoding is entirely hidden while the GPU is doing its work, you actually don't see this as a total overall cost in your implementation itself.
Okay. Any other questions? Those are the questions that I received in the chat. There is yes.
One question. There is one question in the QA box. Basically, someone is saying, do you assume trust in DarKnight?
Say that again.
The question says, do you assume that DarKnight is trusted, or do you assume that you trust DarKnight?
Yeah, so the DarKnight is the system that is actually doing this whole computational sequence. And the only trust that we have, and I think if I understand the correct question, the question correctly, I believe the question is asking, do I trust the trusted enclaves themselves correctly to do the correct work? This is, of course, a limitation in the sense that if Intel tells us that enclaves are trusted and enclaves are a hardware mechanism, there are existing papers that actually verify that claim. We assume that the enclaves or SGX is in fact trusted. And once enclave is trusted, this entire computational fabric that we were talking about, which is this idea that we can do all of these computations, can be trusted. And of course, they will become trusted as well. Yes.
Okay. We have another question here. It says that trusted execution environment in the server. We assume that the trusted execution on the server or on the client side.
We actually assume that the trusted environments are actually on the server side. So you only send the images to the cloud and let the cloud do all of its computations and then send the data to the GPUs. And hence, in some sense, it's actually beneficial to use this approach, because if you look at this picture here, the GPUs are attached to the enclave and the client is separated from the GPUs. And hence this computation, this communication between the client and parameter server or the cloud is through standard interfaces like Wi-Fi, Ethernet, and things of that nature. The communication channel between the servers and the GPU is much faster. So this could be InfiniBand and so on.
So the communication between the GPUs and the trusted execution environments are local communication within the
They are local communication within the cloud server itself. So it could be like, say, PCIe or some kind of InfiniBand switches, or could be NVLink like switches. So this is much faster communication than this communication, and therefore I think the questioner is actually correct in the sense that one could do this encoding within the client and only communicate directly with GPUs, but then the cost of like transferring data would be quite slow. Okay.
There is a question here, Dr. Navarro says that this encoding and decoding is like genotype and phenotype in GA?
This is outside of the knowledge base that I have. I'm not exactly sure if I can answer that question because I don't know enough about the literature to say exactly how it is performed in other GAN architectures.
There is also another question about the memory limitation. How is the memory limitation that the 128 megabyte of enclave has been accounted for in the DarKnight? Well, does it affect the execution of the DarKnight in the TE?
Yeah, it's a good question. So two things. One is, remember, W is no longer private. It's actually, W is always a public information. So the model itself is public. So the models can actually directly stay on the GPU. They don't actually come to the parameter server. They don't go inside the SGX. They're actually on the GPU. So that's one. Therefore, we reduce that constraint. Second, what does the parameter server or the SGX need to keep secret? So if you remember, what does it need to keep secret? It needs to keep secret. So let's go back here. It needs to keep secret this matrix A. But the matrix A is a very small matrix. It's just scalar numbers like alpha ij, alpha 11, alpha 12. And it also needs to keep track of the random noise R. So those must be kept secret. And what else must be kept secret? The input images and the intermediate features must also be kept secret. And therefore, it is the reason why we, in my example, I only picked 4 images, is a limitation that if you go more than 4 images, you need to keep a lot more information inside the SGX. And therefore, we limit the number of images that I can fuse to some reasonable number that your enclave is going to handle. And that could be, 4, maybe 5 images, something like that. And then if you have, let's say, 128 images, you divide them into batches of 4 and you process them 4 at a time to deal with the memory limitation of the SGX.
Dr. Flimban has a question.
Yeah, I have a question, Professor Navarro. First of all, thank you for the nice presentation. I think you answered my question somehow. My question was about the input images. You said they are secret, so they are not known to the, let's say, the malicious or the adversary, right? Okay, I see. So what is the threat model that you are assuming on the GPU? So the GPU are the adversary, right? So
the GPUs are anything outside of the, so the threat model that I'm assuming is basically this, that I trust this person, I don't trust the GPUs. And this person is the enclave. So I trust the enclave and I don't trust anything outside of the enclave.
I see. So how do you trust that, let's say the adversary who runs the, owns the GPU, for example, can, for example, submit certain images to the enclave in a sense that if he can arrange the images somehow, he can infer something about the secret matrix A?
Good question. So remember, it's very easy, right? I gave you the example of the matrix, secret matrix A with respect to a set of 4 images. But for every set of 4 images, I have a different alpha A matrix that I generate, and I give out a different A every single time. And therefore, as long as I'm not reusing those matrix A random variables across different batches of images, and let's say I pre-generated millions of these random variables that I pick as my collection for matrix A, and I have pre-generated A transpose inverse, then I don't disclose. So you're correct that if I really reuse those values of matrix A multiple times, there is some leakage potentially, because the GPUs can say, let me send these 4 images, let me send the next 4 images, and then I might be able to extract something more from them.
Exactly, I see. Okay. So one more follow-up question. You mentioned about the perfect secrecy in terms, which is basically information theoretic. How do you, let's say, how do you prove that, or how do you, show that?
So the proof actually is in the fact that I don't think I have a slide on it, but the basic principle is the following. Our claim is that x prime, as computed in this equation, has 0 information about x1 or x2 or x3 or x4 or x5. And the idea here is that by multiplying with random scalars and adding a completely random noise alpha 1.5 times r, we actually guarantee, and the theoretical proof is actually in the paper, it's a little bit lengthy, but it actually talks about how this is equivalent to getting a one-time pad like privacy or security. In other words, this data has no mutual information with respect to all the input images that I have.
Okay, so the secret A is you prove that it is completely independent from the input image.
Exactly. That's in fact, that's exactly correct. In fact, matrix A and matrix R are independent of the 4 input images, and therefore there is no dependency between those 2 sets of random variables and the input information itself.
Excellent, I see. One last question. You mentioned the upper bound of M, which are the colluding GPUs. I didn't quite get what is K prime with the batch size. What is
K prime with the batch size? Oh, sure. So what this is saying is, if you look at here, K prime is the number of GPUs that you have.
Okay.
So in my example, 5 is the number of GPUs. K is the batch size. In the example that I gave you, K is 4, and K prime is 5.
I see. So number of pictures.
Number of pictures is the batch size.
I see. Okay, clear. Thank you so much.
You're welcome.
Okay, we have one more question.
Sure.
It asks about if is the alphas, the matrix A and R, secret from the GPU, then encoding and decoding is not an actual encryption decryption. Do you agree with that?
So Abdulaziz, could you please repeat the question?
Yeah, it says that is alpha and R are secret. The alpha, the A matrix and R are secret from the GPUs. Then the encoding and decoding is not an actual encryption or decryption. If the alpha and R.
Yeah, in fact it is not it's not an encryption decryption strategy. It's an encoding decoding strategy, and therefore I want to make sure that the process by which we are generating these values is not using any kind of encryption mechanism, but it's using encoding mechanism, which is different, right? Because basically just sort of doing some sort of scaling of the inputs to an adding of random noise, which is not the same as actual encryption decryption. So we do not protect using encryption decryption, but we are using encoding decoding, which is actually a mechanism for which, because the problem is, if I encrypted the data and I computed on it, it will become homomorphic encryption mechanism, which has a lot of overheads and very, very slow. Whereas what we are doing is the GPU-based computations on encoded data. And as long as I can decode it, I'm good to go.
Okay. One last question here. The question says that, can we say that DarKnight is an example of how cloud should be leveraged in the future for training machine learning models?
Well, I mean, obviously we would love to. And so We have been working with multiple companies, including Facebook and other companies, to sort of see if there is a way for us to bring it to practice. Because one of the questions that people did not ask, which I guess many times I get asked, is, how slow is this system compared to I don't care about privacy system, right? Basically, run everything on the GPU. I showed you what is the baseline, which is run everything on the TEE. We are still 10x slower than running everything on the GPU. But compared to running everything on the GPU today, if you want to run everything on the TEE, it's 100x slower. So we kind of, on the logarithmic scale, we went to halfway point. So what we need is to improve the efficiency a little bit more. And that's where in future talk, we have been looking at how do you selectively protect data, not all the data, if there's a mechanism to separate out the features that are secret and not secret. But Abdulaziz, that's a different talk. I'll give you another time.
Okay. Thank you, Professor Navarro, for this wonderful speech. And we're glad to have you today here and to accept our invitation. And hopefully we will see you, inshallah, in the future.
Absolutely.
Thank you all for attending our today's talk. And see you, inshallah, soon.
Okay. Thank you. Thank you, Professor.
Thanks, Mohammed. Thank you very much, everybody.
Have a good day.
You too.